It takes light about 14 minutes to travel from Mars to our eyes. A spacecraft, almost 8 months. The planet itself has waited 4.5 billion years for someone to look up and notice it. Tonight, we are going to spend a little while looking. Let's dive in. For as long as people have looked up at the night sky, Mars has been there. A small, steady ember among the cooler white of the stars. The ancient Egyptians called it Her-Desha, which means simply the red one. The Babylonians named it Nergal, after a god of fire and war. The Greeks gave it the name Ares, and the Romans, watching the same point of light from a different empire, called it Mars, after their own god of war. All of them, on different continents in different centuries, looked up and reached the same conclusion. That colour meant something. That colour meant blood, or fire, or anger. Nothing peaceful had ever been that red. But of course, none of them knew. None of them had any way of knowing. They had no telescopes, no rovers, no spacecraft, no photographs. They had only their eyes, the dark sky, and an unbroken inheritance of curiosity passed quietly from one generation to the next. Before we go any further, if you find your shoulders softening as you listen, consider giving this video a like. It helps more sleepy travelers find their way here. Subscribe if you'd like to come back for more nights like this one. And in the comments, you can tell us the city you're listening from, so the rest of us can imagine the lights of your window turning off, somewhere far away. What those ancient watchers were really seeing, though they couldn't have known it, was a world. Not a god, not an omen. A world with mountains and plains and weather of its own. Mars is the 4th planet from the Sun, sitting just beyond Earth in the slow procession of orbits. On a clear night, when it rises eyes above the horizon, you can find it with no equipment at all. Just step outside. Let your eyes adjust to the darkness, and look for the one that doesn't quite twinkle. Stars shimmer because their light is so faint and so distant that the air bends it as it falls. Planets, being closer, hold steady. They glow rather than flicker. Mars glows in a quiet, copper-rose colour, like a coal that has been burning a long time. For thousands of years, this small red ember was a puzzle. It didn't behave like the other stars. It moved against the background of the constellations in a strange, looping path. Sometimes it would slow down, stop, and appear to travel backwards across the sky for weeks before resuming its forward motion. This is called retrograde motion, and it confused astronomers for centuries. Ptolemy, in the 2nd century, built an elaborate system of circles within circles to explain it. It took nearly 1500 years before Johannes Kepler, sitting at a desk in Prague with pages of careful observations, finally worked out the truth. Mars wasn't looping. Earth was simply passing it on the inside of its orbit, the way a faster car overtakes a slower one on a highway. The strange backward motion was an illusion, a trick of perspective. That moment, in the early 1600s, was when our understanding of the solar system quietly changed. Mars, in a sense, gave us the shape of everything else. It taught us that planets orbit in ellipses, not perfect circles. It taught us that Earth was not the centre of anything in particular. And once that one small red point of light had given up its secret, the rest of the sky began, slowly and gently, to make sense. Tonight, That same light is still up there, the same color the Egyptians named, the same ember the Babylonians feared, still waiting in its patient orbit for whoever happens to look. The distance between Earth and Mars is never the same twice. If you measured it tonight, then measured it again next month, you would get different numbers, different by millions of kilometers. Both planets are moving, after all. Both are tracing their own slow ellipses around the Sun at different speeds, on different timetables. Earth completes a lap every 365 days. Mars takes 687. So the gap between us is always changing, always closing or opening, like two runners on a wide circular track who never quite meet at the same spot twice. On average, Mars sits about 225 million kilometers away. That is the number you see in textbooks. The polite, rounded answer. The truth is more interesting. When Earth and Mars line up on the same side of the Sun, the gap closes to around 55 million kilometers. That alignment is called opposition, and it happens every 26 months or so. When the two planets are on opposite sides of the Sun, the gap widens to roughly 400 million kilometers. That is called conjunction. The same two planets, the same orbits, but the distance between them can shift by almost a factor of 8, depending on the month. To put 225 million kilometers in some kind of human scale, imagine driving there at highway speed, 60 miles an hour, never stopping, never sleeping. You would arrive at Mars in about 270 years. A car that began the trip in 1755, before the American Revolution, before electricity was understood, but before anyone alive today was born, would just be pulling in now. Spacecraft do better than highway speed, of course. They use the Sun's gravity. They follow elegant curved paths called Hohmann transfer orbits, worked out by a German engineer named Walter Hohmann in 1925, decades before anyone could test them. A Hohmann transfer is the most fuel-efficient way to move between two orbits, and it traces a long, lazy ellipse from Earth to Mars. The trip takes between 6 and 9 months, depending on how the planets are positioned at launch. Perseverance, the most recent rover to land, took just over 6 months. Curiosity, before it, took 8.5. There is something quiet to consider here. When you look up at Mars tonight, you are not seeing it as it is. You are seeing it as it was. Light travels at a finite speed, just under 300,000 kilometers every second, and even at that speed, it takes time to cross the gap. Depending on where the two planets are in their orbits, the light reaching your eyes left Mars somewhere between 3 minutes and 22 minutes ago. 3 minutes when the planets are closest, 22 minutes when they are farthest apart. Right now, this very second, whatever Mars is doing, you cannot see it. You can only see what it was doing several minutes ago. The dust storms, the sunrise lines crossing its surface, the faint frost on its rocks, all of it reaches you slightly late, like a letter that took some time to travel. This is true of every star and planet in the sky, but Mars is close enough that the delay is small. You are looking at a recent past, not an ancient one. The light from the more distant stars left them centuries or millennia ago. Some of the stars you see at night may not exist anymore. They burned out long after their light began the trip toward your window. But Mars is just a few minutes behind. Whatever it is doing tonight, you will know about it soon. There is something steadying in that. The universe is full of distance, full of delay, and yet, even across hundreds of millions of kilometers, the light still finds its way to you, quietly, patiently, on its own schedule. That light, when it finally arrives, carries a particular color. Not just brightness, but a specific shade, a coppery, rusted hue, like an old gate that has been left out in the rain for too many seasons. And what you are seeing at that great distance is exactly that. Rust. Mars is, in a literal sense, a rusted world. Its surface is rich in iron oxide, the same compound that forms when iron meets oxygen and water on Earth. It is what flakes off old cars and stains the rocks around a leaky pipe. Across an entire planet's surface, this thin coating of iron oxide is what gives Mars its color. If you could scoop up a handful of Martian soil and bring it home, it would look, at first glance, like rusty garden dirt. The dust itself is unbelievably fine, far finer than anything you would call dust on Earth. The particles are often only a few micrometers across, smaller than flour, closer in scale to cigarette smoke, and there is a great deal of it. The planet is wrapped in a layer of this rust-colored powder, in places several meters deep. It coats the boulders, fills the cracks, and settles into every shaded hollow. When a rover lands, the first thing it does is leave footprints in it. But here is the part that has puzzled scientists for a long time. Rust on Earth needs water and oxygen to form. Mars has almost no oxygen in its atmosphere today, and no liquid water on its surface. So how did an entire planet get rusted in the first place? For decades, the leading theory was that the iron oxide formed slowly and dryly over billions of years through a kind of chemical weathering that did not require much water. But in 2025, a team of researchers studying data from multiple Mars missions published a different answer. The specific kind of iron oxide making up the red surface, they found, is ferrihydrite, and ferrihydrite on Earth only forms in the presence of liquid water, cool, slightly acidic water, the kind that would have been pooling on the Martian surface long ago, when the planet had rivers and lakes. In other words, the dust that gives Mars its color may be a chemical fingerprint of an ancient, wetter world. A world that no longer exists except in this faint orange coating that the wind keeps lifting and moving and laying down again. That wind matters. Mars has a very thin atmosphere, only about 1% the density of Earth's, but it is still enough to move dust around. Over centuries, the wind has scattered the iron oxide everywhere. It piles up in dunes and gathers in craters. It rides up drafts and stays suspended in the air for weeks or months at a time. There is almost always some dust in the Martian sky. This is why daytime on Mars does not look like daytime here. When the sun is high overhead and you look up, the sky is not blue. It is the color of butterscotch, soft and warm and slightly pink, like the inside of a seashell, or the light coming through a paper lampshade. The suspended dust absorbs the bluer wavelengths and lets through the warmer ones, so the whole sky takes on that pinkish glow. You would notice it on your skin, on the rocks, on everything in sight. Photographs from the rovers show it clearly. The ground is a dusty cinnamon. The shadows are softer than Earth shadows. The horizon fades into a haze, the colour of a sunset that never quite leaves. It is a quieter kind of daylight. The sun is smaller in the Martian sky, because Mars is farther from it, and solar light arrives with about half the intensity that we get on Earth. Combined with the dust in the air, this gives the whole landscape a perpetual late afternoon feeling, even at noon. The colour we see from our own window, that small coppery point low in the sky, is in some sense the same colour that someone standing on the surface of Mars would see in every direction, from the rocks beneath their feet to the horizon ahead of them to the sky overhead. A whole planet wearing one colour, breathing it back out into space, where eventually some of it travels far enough to reach a small blue world, and a window, and a pair of eyes that happen to be looking up. The wind that lifts that dust is moving through almost nothing. Mars has an atmosphere, but it is one of the thinnest you could find around any planet that has one at all. The air pressure at the Martian surface is roughly 6 millibars. On Earth, at sea level, the air pressure is just over 1,000. That makes the Martian atmosphere less than 1% as dense as the air outside your window right now. If you stood on Mars without a suit, the air would not be the first problem you noticed. It would be there. It just would not be enough. The composition is mostly carbon dioxide. About 95% of the Martian atmosphere is CO2, the same gas you breathe out. The rest is a quiet mix of nitrogen, argon, a trace of oxygen, and a faint whisper of water vapour. There is more argon in the Martian air than in Earth's. Argon is inert and unreactive. It simply lingers, century after century, while other gases escape into space. Because the air is so thin, it behaves in strange ways. Take wind. The strongest Martian winds, measured during the largest global dust storms, can reach about 60 miles per hour. On Earth, that is the wind of a tropical storm. It would tear off shingles, snap branches, and send patio furniture flying. On Mars, that same wind would feel like a faint breath against the skin, maybe a passing exhale, almost nothing. The reason is simple. Wind only pushes as hard as the air it is made of, and Martian air is barely there. A 60-mile-per-hour wind on Mars carries about the same force as a 6-mile-per-hour breeze on Earth. The dust storms that blanket the planet look ferocious from orbit, with curtains of orange spreading across hemispheres. But standing inside, one would feel oddly gentle. The dust would arrive in slow waves. The flags on a rover would tremble, not flap. Sound behaves differently too. In 2021, the Perseverance rover carried microphones to Mars and recorded the first audio ever captured on the surface of another planet. What it captured was a quiet world. Sounds travel more slowly through Martian air, around 240 meters per second instead of the 343 we are used to on Earth, and they fade faster. The thin atmosphere absorbs high frequencies almost immediately, so anything that would have been a sharp crack on Earth becomes a soft thud on Mars. A conversation between two people standing 20 feet apart would be barely audible. A song would lose its top notes within a few seconds. Whatever you said into that air, the air would swallow most of it. Water has its own quiet problem. The atmospheric pressure is so low that liquid water cannot stay liquid for very long on the surface. The boiling point depends on pressure, and at 6 millibars, water boils at temperatures just above freezing. So if you spilled a cup of water on Martian soil at noon, it would not soak in or pool. It would fizz briefly, then either evaporate into the air or freeze into the ground, depending on the exact temperature. The same molecule that fills our oceans and rivers cannot really exist on Mars in its familiar form. It only passes through, going from solid to vapor and back, skipping the middle entirely. And yet, the air is real. It moves. It blows dust across the dunes and gathers into thin morning fogs in the deep canyons. It carries the high-altitude clouds that hang sometimes above Olympus Mons. It thickens and thins with the seasons, because carbon dioxide actually freezes onto the polar caps every winter and lifts back into the atmosphere every summer. The whole planet breathes in its own slow way. The pressure rises and falls by as much as 30% over a Martian year, simply because of the cold trapping and releasing gas at the poles. Standing on the surface with the right suit, you would not feel weather the way you feel it here. No gust would knock you off balance. No rain would fall on your visor. Sound would arrive faint and stripped of its sharper edges. The whole atmosphere would feel like the memory of an atmosphere, present but mostly silent, brushing past you on its way to somewhere else. It is an air that does very little, but it has been doing it for a long time, and it is still there tonight, moving slowly above the rust. But once a day, that thin air does something extraordinary. If you were standing on the rust-coloured ground at the right moment, just before nightfall, you would notice the light around you beginning to change. The horizon would dim as it does everywhere. The shadows would lengthen. The temperature would drop fast, and then, in the part of the sky where the sun was setting, a strange thing would happen. The pinkish butterscotch colour of midday would peel back, and in its place, around the small white disk of the setting sun, a deep, soft blue would bloom. Blue, on a planet that has never known a blue sky in living memory. In the one part of the day when, by every earthly instinct, you would expect warm orange and red. This is the most famous and counterintuitive image in planetary science. It has been photographed by spirit, by curiosity, and by perseverance. The Martian sunset is blue. The reason has to do with the dust again, but in reverse. On Earth, the sky is blue during the day and red at sunset because the atmosphere itself scatters short blue wavelengths more strongly than long red ones. That is a process called Rayleigh scattering, and it happens because the molecules of the air are smaller than the wavelengths of visible light. During the day, blue light bounces around the sky and reaches your eye from every direction, so the sky looks blue. At sunset, when the light has to travel through more atmosphere to reach you, the blue gets scattered away long before it arrives, leaving the warmer reds and oranges. On Mars, the dust particles in the air are larger than the wavelengths of light. That changes the physics. The same dust that makes the daytime sky pink, because it scatters red light in all directions, also scatters blue light more strongly forward, in a narrow cone around the sun. So, during the day, with the sun overhead, the diffuse pinkish glow fills the sky. But when the sun gets low and the light has to push through a thicker column of dust to reach you, blue is the wavelength that survives best in the direction of the sun itself. The result is a soft, glowing blue circle around the setting sun, against a sky that is otherwise the colour of a faded peach. There is no painting of this that quite captures it. You almost have to see the rover photographs yourself. The sun, smaller than the one we know, only about 2/3 its size in the sky, sits on the rim of the horizon. Around it, a halo of deep blue. Behind that, a wash of dusty orange. And the rocks in the foreground, the same rusted cinnamon you have been looking at all day, are now lit from the side, casting long blue-tinged shadows toward the camera. A Martian sunset also lasts longer than ours. The dust, suspended high in the atmosphere, catches the sun's light long after the sun itself has dropped below the horizon, and the sky stays softly lit for 2 hours or more after sunset. There is a long, patient twilight, slow enough to walk through. Slow enough if you happen to be there to stand at a window and watch the blue fade out of the sky on its own gentle schedule. It is one of those small details that turns Mars from a number on a chart into a place. A real place, with weather and light and an end-of-day quietness that anyone alive on its surface, if anyone ever were, would recognize. A red world, a pink sky, a blue sunset, and then, slowly, dark. The largest mountain in the solar system stands on Mars in a region of high volcanic plains called Tharsis. Its name is Olympus Mons, and it is the tallest known volcano of any kind on any world, from its base on the flat plain to its summit at the center of its caldera. It rises about 21.9 kilometers into the sky. That is nearly 2.5 times the height of Mount Everest, which, by Earth standards, is already an extraordinary number. But the height is not really what makes Olympus Mons strange. The strangeness is in the shape. If you were dropped onto the slopes of Olympus Mons, you would not feel like you were on a mountain. The slopes are extremely gentle, averaging only about 5 degrees. That is roughly the steepness of a wheelchair ramp. You could walk up it for days without realizing you were climbing anything at all. The base of the mountain is so wide, about 600 kilometers across, that it would cover roughly the area of the state of Arizona, or all of Italy. And that is the heart of it. Olympus Mons is not a mountain in the way. Everest is a mountain. It is a continent that happens to be raised up at the middle. Its width is more than 25 times its height. From any point on its slopes, the summit is hidden, not just by clouds or dust, but by the curve of Mars itself. The horizon falls away before the peak comes into view. A person standing on the side of Olympus Mons could not, in any direction, see the top. The caldera at the summit, where the volcanic vent once was, is itself a basin about 80 kilometers wide. You could fit a small city inside it, and around the entire base of the mountain runs a cliff, the Olympus Mons escarpment, that is in places 6 kilometers tall. 6 kilometers of vertical rock face, a wall as high as some of the deepest canyons on Earth, simply marking where the volcano ends and the plain begins. Olympus Mons is what called a shield volcano. It was built up, layer by layer, over billions of years, as lava flowed out of a vent in the surface and spread in thin sheets across the surrounding land. On Earth, volcanoes like this exist too. Mauna Loa in Hawaii is a shield volcano, but on Earth, the crust is broken into plates that move slowly across the planet's hot interior, and so a hot spot beneath the surface eventually produces a chain of volcanoes, like the Hawaiian Islands themselves, as the plate slides over the source. Mars does not have plate tectonics. The crust does not move. Whatever hotspot fed Olympus Mons stayed in place for hundreds of millions, perhaps billions, of years. Lava kept arriving in the same spot. The mountain kept growing. There was nothing to interrupt it. That is why it became so enormous. It is a record of patience, written in basalt. Olympus Mons may not be entirely extinct. Some of its lava flows look young enough, geologically speaking, to suggest eruptions as recently as a few million years ago. By the standards of a 4.5 billion-year-old planet, that is recent. The mountain might still, in some quiet sense, be sleeping rather than gone. The summit reaches above most of the Martian atmosphere. At the top of Olympus Mons, the air pressure is only about a tenth of the already thin pressure at the planet's average surface. Most of the dust that gives Martian daytime its butterscotch glow lies in the lower atmosphere beneath the summit. So the air at the peak is nearly clear, and the sky overhead approaches the blackness of space. Imagine that, a mountain so tall that if you stood at its summit, you would already be partway into the sky. And yet, from the ground at its base, you would never know it was there. The slope would simply rise away from you, gentle and patient, until it disappeared over the horizon, like a hill that never quite ends. Just east of Tharsis, where Olympus Mons rises out of the lowlands, the ground does the opposite. It splits open and drops away into one of the most extraordinary scars on any planet in the solar system. Its name is Valles Marineris, the Valleys of Mariner, named for the spacecraft that first photographed it in 1971. And it is a canyon system that beggars comparison to anything on Earth. Valles Marineris runs roughly along the Martian equator for more than 4,000 kilometers. That is the distance from New York to Los Angeles, or from Lisbon to Moscow. End to end, it would stretch across the entire continental United States, and still have hundreds of kilometers to spare. In some places, it is 200 kilometers wide. In others, the walls plunge as much as 7 kilometers below the surrounding plain. To put that in some kind of scale, the Grand Canyon in Arizona is about 446 kilometers long, 30 kilometers wide at its widest, and a bit less than 2 kilometers deep. You could fit 10 Grand Canyons end to end inside Valles Marineris, with room to spare. You could drop the Grand Canyon into Valles Marineris, and it would be a side channel, but length and depth are not the only differences. The Grand Canyon was cut by water. The Colorado River, over millions of years, slowly carved its way down through layers of rock, deepening as the surrounding land rose. Valles Marineris was not made that way. It was not cut by a river. As far as anyone can tell, it was cracked open by the planet itself. The story goes back to Tharsis, the bulge that Olympus Mons sits on. Tharsis is an enormous, raised region of the Martian crust, lifted up by the same long history of volcanism that built Olympus Mons. As Tharsis rose, the crust around it stretched. East of Tharsis, that stretching pulled the surface apart. It tore, and the tear is what we now call Valles Marineris. It is, in a sense, the crack on the side of a slowly inflating balloon. Smaller forces have shaped its details since then. There are places within the canyon where landslides have piled rubble onto the floor. There are smaller chasms branching off the main valley that show signs of having held water at some point, possibly seeping up from the ground. There are layers in the canyon walls that record different episodes in Martian climate, like the stripes you see in road cuts on Earth, where a hillside has been sliced through. If you stood on the rim of Valles Marineris and looked across, you might not see the other side. In its widest sections, the opposite wall is so far away that it falls below the curve of the planet's horizon. You would see only your own rim, falling away in tiered cliffs, and then a hazy gap, and then nothing. If you stood at the bottom of one of the deepest sections, you would be 7 kilometers below the surface above you. The air pressure down there is actually a little higher than the planet's average, because pressure increases with depth, the same way it does in the deep ocean on Earth. Some scientists have suggested that, in the distant past, the bottom of Valles Marineris may have been one of the few places on Mars where water could pool as a liquid for any meaningful amount of time. A long, narrow lake at the floor of the largest valley in the solar system. Today, none of that water remains. The canyon is dry. The wind moves through it slowly, raising small dust trails that travel for hours along its length. Once a year, when the planet enters its warmest months, frost forms on the shaded northern walls. By midday, it is gone again. Valles Marineris is the kind of feature that makes you understand, in a single image, how different Mars is. Olympus Mons shows you what the planet has built. Valles Marineris shows you what the planet has broken. Both took billions of years. Both are still there, more or less, exactly as they were the last time anyone managed to look. If you stood at the bottom of Valles Marineris in the early evening and looked up, you might see, racing across the sky, a small, lopsided shape. Mars has 2 moons. Both of them are tiny. Both of them look more like asteroids than moons. And one of them is doing something no other moon in the solar system does. The larger of the 2 is called Phobos, named for the Greek god of fear, the son of Ares, the god of war. It is the inner moon, the one closer to Mars. Phobos is only about 22 kilometers across, irregularly shaped, lumpier than a moon should be, like a potato that has been knocked around inside a bag. Its surface is cratered, dusty, and dark. Phobos orbits Mars at a distance of only about 6,000 kilometers. That is closer than any other moon orbits its planet anywhere in the solar system. The moon, our own moon, orbits Earth at an average distance of about 384,000 kilometers. Phobos sits more than 60 times closer to Mars than that. It is practically grazing the planet's atmosphere because it is so close. It moves quickly. Phobos completes one orbit around Mars in about 7 hours and 39 minutes. That is faster than Mars itself rotates. The planet turns once every 24 hours and 39 minutes. Phobos completes 3 orbits in the time Mars makes one full turn. The result is one of the strangest sights in the solar system. Phobos rises in the west. It crosses the Martian sky in about 4.5 hours, and then it sets in the east. Just a few hours later, it rises in the west again. From the surface of Mars, the inner moon goes the wrong way through the sky, twice a day. Phobos is also fading away. Slowly, almost imperceptibly, it is spiraling inward toward Mars. The tidal pull between moon and planet is pulling it down by a small amount every century, about a meter every 100 years. Over the next 50 million years or so, that slow descent will accumulate. Either Phobos will crash into the Martian surface, or, more likely, it will be torn apart by tidal forces as it gets too close to the planet, and its pieces will spread out into a thin ring around Mars, like Saturn's. Either way, Phobos as it exists now will not be there forever. The smaller moon is called Deimos, named for the god of terror, brother of Phobos. Deimos is even smaller, only about 12 kilometers across. It orbits much farther out, at about 23,500 kilometers from Mars, which puts it in a slower, calmer orbit. Deimos takes 30 hours and 18 minutes to circle Mars once. Because that is slower than the Martian day, Deimos behaves more like our own moon. It rises in the east, sets in the west, and stays in the sky for about 2.5 days at a time. From the Martian surface, Deimos would look like a bright star. It is far enough away that you could not really see it as a disk with the naked eye, only as a point of light. Phobos, by contrast, would be visibly an object, a small, irregular shape, moving and turning slowly as it passed overhead. Where these two small moons came from is still being argued. For a long time, the leading theory was that they were captured asteroids. They have similar reflectance and composition to certain dark asteroids in the outer asteroid belt, and that would make them gravitational hitchhikers, dragged into orbit billions of years ago. But the geometry of their orbits, which sit almost exactly in line with the Martian equator, is hard to explain through capture. Lately, another theory has gained ground. A large impact early in Martian history may have thrown a ring of debris into orbit, and from that ring, the two small moons coalesced. In that version of the story, Phobos and Deimos are the leftover children of an ancient catastrophe. Whatever they are, they keep their quiet company, the inner moon racing the wrong way 3 times a day, the outer one barely moving at all, and below them the patient red landscape, with its canyons and volcanoes and rust turning slowly under the stars. Below those moons, Mars is turning at almost exactly the rate that Earth turns. Almost. A Martian day, measured from one sunrise to the next, lasts 24 hours, 39 minutes, and 35 seconds. To distinguish it from our own day, scientists give it a separate name. They call it a sol. It is one of the most unexpected coincidences in the solar system. Mars is a different planet, in a different part of the sky, made of different materials, with a different gravity and a different history. There is no obvious reason that its day should be only 39 minutes longer than ours. It just is. Mars rotates at almost the same speed Earth does, and that small difference, those extra 39 minutes, has shaped the way humans interact with Mars in a peculiar and quietly poetic way. When a rover lands on Mars, the mission team on Earth needs to keep track of what the rover is doing. The rover has to work during the Martian daytime, when it can use its solar panels, and avoid the worst of the nighttime cold. So the team's job, the daily planning of where the rover will roll and what it will photograph, has to follow Martian time, not Earth time. The team has to live on Mars time. For the first several weeks of a Mars mission, this is often what happens. The engineers and scientists running the rover shift their lives by 39 minutes every day. They go to bed 39 minutes later. They wake up 39 minutes later. They eat dinner 39 minutes later. Over the course of a few weeks, they slowly walk their schedule around the clock. A team member might start a mission going to bed at midnight. A week later, they are going to bed at 4:30 in the morning. Another week, and they are going to bed at 9 a.m., while everyone they know is on their way to work. Their children are at school, the sun is shining, and they are asleep on a planet's schedule that does not match the one outside. Eventually, their bodies adapt. They begin to feel hungry on Martian time. They begin to feel tired on Martian time. Their internal clocks, which evolved over hundreds of thousands of years to track the Earth's 24-hour day, slide quietly off the edge. There are stories from the early Mars rover missions of engineers walking around the Pasadena campus of NASA's Jet Propulsion Laboratory at 3 in the afternoon, wearing watches set to a planet 225 million kilometers away. There were Mars time wristwatches custom made for them, ticking 39 minutes slower per day than the watches on every other wrist in the building. There were curtains taped over kitchen windows so that morning light would not confuse a brain trying to think it was still night time. Meals were eaten when the rover was sleeping. Sleep happened when the rover was working. Most teams give up after about 90 sols. Mars time is exhausting. It pulls you out of sync with your family, with your meals, with sunlight itself. The body never quite gets comfortable. But for those first 3 months, there is a strange privilege to it. You are, in some real sense, living on Mars. The 39-minute difference comes from a slight mismatch in rotation rates. Mars turns just a little more slowly than Earth, by about 2.5%. That percentage, when applied to the length of a day, comes out to about 39 minutes. Multiplied over a Martian year, it adds up to more than 200 hours of extra rotation. Mars makes about 668 full rotations in the time it takes to orbit the Sun once, where Earth makes about 365. But on the surface, in real time, the difference is small. Sunrise on Mars looks like sunrise on Earth, only quieter. The light comes up over the same kind of horizon. The shadows lengthen and then shrink the same way. The afternoon has the same drowsy weight to it, somewhere in the middle of every Martian soul, when the sun is highest and the dust settles in the air. If you lived on Mars, you would notice the extra 39 minutes only because, every once in a while, you would wonder why dinner felt slightly later than it should. And then, like the engineers in Pasadena, you would simply adjust. If the day is almost same, the year is not. Mars takes 687 Earth days to make one complete orbit around the Sun. That is just under 2 Earth years, about 1 year and 10.5 months. So if you celebrated your birthday on Mars and waited for the same date to come around again, you would wait nearly twice as long as you would on Earth. The reason is straightforward. Mars sits farther from the Sun than we do in a wider orbit. The distance from Mars to the Sun averages about 228 million kilometers, where Earth's distance averages about 150 million. A larger circle takes longer to travel around. Add to that the fact that Mars also moves more slowly than Earth does, because the Sun's gravity is weaker at that distance, and the result is a year that takes almost twice as long. That has a particular effect on the seasons. Mars has seasons for the same reason Earth does. Both planets are tilted on their axes as they orbit. Earth's axis tilts at about 23.4 degrees. Mars tilts at about 25.2 degrees. The numbers are very close. This means the rhythm of the seasons on Mars is recognizable. There is a spring, a summer, an autumn, and a winter. The poles tilt toward the sun for half the year and away for the other half. But because the year is twice as long, each Martian season lasts about 6 Earth months. A Martian summer is half an Earth year. A Martian winter is half an Earth year. Spring rolls around like a slow tide. If you wanted to wait out a Martian autumn before it gave way to the cold, you would wait nearly as long as a baby on Earth takes to learn to sit up. There is something else that makes the seasons on Mars stranger than ours. Mars has a more eccentric orbit than Earth does. That is to say, its orbit is more egg-shaped than circular. There are times of the Martian year when Mars is significantly closer to the Sun, and times when it is significantly farther. On Earth, the orbit is near sea-circular, so the difference between our closest and farthest points from the Sun is small. On Mars, it is more dramatic. This means that the southern hemisphere of Mars, which tilts toward the Sun when Mars is closest to it, gets shorter and hotter summers. The northern hemisphere, which tilts toward the Sun when Mars is farthest from it, gets longer and milder summers. Southern winters, conversely, are longer and colder than northern winters. The hemispheres do not experience the year evenly. One side of the planet runs hot and short, the other side runs cool and long. This is not just a curiosity. It is the engine that drives the dust storms. The southern summer, hot and rushed, sends more energy into the atmosphere than the northern summer does. That extra energy stirs up the dust. The biggest global dust storms on Mars almost always begin in the southern hemisphere, in the southern spring or summer, when the sun is closest and the temperature gradient is steepest. If you lived a human lifetime on Mars, you would experience much less of it in years. A person who lives to be 80 on Earth has lived through 80 trips around the sun, 80 cycles of spring and summer and autumn and winter. If that same person lived 80 Earth years on Mars, they would have completed only about 42 Martian years. They would have seen the seasons cycle 42 times instead of 80. There is something strangely peaceful in that thought. To live a long life and have it measured in fewer years. To experience long summers that last 6 months, long winters that last 6 months, long autumns where the light slowly cools and the dust slowly thickens. A life on Mars would feel slower in some quiet way, not because anything had actually slowed down, but because the calendar had grown longer to match the bigger orbit. The point of light you see at night, the small coppery ember, is moving as we sleep, slowly. About 24 kilometers every second. That is how fast Mars travels around the Sun. It is as leisurely speed by planetary standards. Earth moves at nearly 30. The difference is part of what makes the year longer. Mars is on a wider road, taking it at a slower pace. A year and 10.5 months. 2 springs in the time we get one. A long, patient calendar. Where this long Martian year shows itself most dramatically is at the poles. Like Earth, Mars has two polar caps, one at the top, one at the bottom. White, frozen, bright enough to see from a backyard telescope on Earth, even though they are 225 million kilometers away. Astronomers in the 17th century, pointing their first lenses at Mars, could already see these caps as small white spots on a red disk. They knew almost nothing about what those spots were. They could tell that the spots changed size with the seasons, growing in winter and shrinking in summer. The simple, beautiful conclusion was correct. Mars has ice. The Martian polar caps are made of two different kinds of ice. Most of the permanent material at both poles is water ice, the same substance that makes up the icebergs and glaciers of our own world. Layered on top of the water ice, especially during winter, is a different kind of ice. Frozen carbon dioxide, dry ice. This second kind is what creates the planet's seasonal breathing. When the long Martian winter arrives at a pole, temperatures fall low enough for the carbon dioxide in the atmosphere to freeze directly out of the air onto the polar surface. The cap grows, the atmosphere thins. When the long summer arrives, the dry ice sublimates back into gas and rejoins the atmosphere. The cap shrinks, the atmosphere thickens, the whole planet inhales and exhales over the course of every Martian year, with the cold poles doing the breathing. The southern cap, in particular, is famous for its strange ice. Underneath its dry ice surface, parts of the southern cap have what scientists call Swiss cheese terrain. Smooth, rounded pits eaten into the ice as it sublimates, the way bubbles form in a slowly melting popsicle. Spacecraft photographs of these regions look almost like coral. Soft circular hollows, hundreds of meters across, scattered across a white-grey surface. The northern cap is bigger. It is the older, deeper, more substantial reservoir of frozen water on the planet. If you could fly above it, you would see something that does not exist anywhere on Earth. Spiral troughs, long curving channels cut into the ice cap, all rotating in the same direction around the pole, like the arms of a slow galaxy. They were formed over millions of years by wind and sublimation, working together as the ice slowly built up in layers. The volume of water locked in the Martian polar caps is enormous. If you melted all the water ice there and somehow kept it liquid, it would be enough to cover the entire surface of Mars in an ocean several meters deep. Some estimates put it higher, on the order of dozens of meters, depending on how much subsurface ice you count along with the surface caps. It is one of the largest known reservoirs of water in the inner solar system outside of Earth. This matters for more than curiosity. Future missions to Mars will almost certainly need water. Drinking water for the people who go. Water to grow food. Water that can be split into oxygen and hydrogen for breathing and for fuel. There is enough water at the Martian poles to support a settled human presence for any timescale we care to imagine. The water is, in that sense, already there. It is just waiting at the poles, in slow patient layers, in the cold. The ice is layered, by the way, carefully, like the rings of a tree. Each polar cap has dozens of distinct horizontal layers within it, each one representing a particular climate epoch in Martian history. Brighter layers and dustier layers, thicker layers and thinner layers. A core sample drilled from the North Martian polar cap, if anyone ever takes one, would tell us in detail what the planet has been doing, climatically, for the past few million years. It would be the most useful book of climate history outside of our own ice cores on Earth. For now, those layers sit untouched, sealed under their own seasonal coating of dry ice. The pole spends its winter in darkness, sometimes for months on end, with no sunlight at all. And in those long polar nights, the carbon dioxide settles out of the sky, onto the surface, very slowly, building up the cap that will sublimate back into the air when the spring finally comes around again, half an Earth year later. A planet breathing through its poles, a long slow inhale, a long slow exhale, once a year, far from the poles where the seasonal ice is measured in kilometers. Mars has its own quieter version of ice, smaller, more fleeting, frost, almost everywhere on the planet. When the long night cools the ground enough, a thin layer of frost can form. It does not stay, it does not pile up. It appears in the early morning, lying in pale lines across the rocks and in the low places where the cold has settled. And within an hour or two of sunrise, it is gone, sublimated, lifted back into the air without ever having melted. You can see this in rover photographs. The Viking 2 lander, way back in 1979, photographed water frost on the Martian surface in its second year on the planet. The Phoenix lander, decades later, in 2008, sat on the Martian Arctic plain and watched frost form on its own legs and footpads, then watched it vanish in the morning sun. The frost is mostly water ice, with some carbon dioxide ice mixed in, depending on the season and the location. It is very thin, often just a few microns. A coating, really, more than a layer. If you brushed your gloved hand across a frosty Martian rock, the hand would come away dry. The frost would have already changed back into vapor by the time you finished the motion. But frost is not only a polar phenomenon. It can form anywhere on Mars where the conditions are right. In the bottom of deep craters at high latitudes, in the shadows on the north-facing walls of cliffs, in the cold, low places where the wind never quite reaches, and, in one of the more surprising discoveries of recent years, frost has been found in a place no one expected. In 2024, scientists analyzing images from European Mars orbiters reported that water frost had been spotted on the summits of the giant Tharsis volcanoes: Olympus Mons, Arsia Mons, Ascraeus Mons, the tallest mountains on Mars, in the middle of the warm equatorial belt. This was not supposed to happen. The volcanoes are near the Martian equator, where temperatures, even in winter, were thought to be too warm for water frost to survive. But the summits of the Tharsis volcanoes reach so high into the atmosphere, into air so thin and cold, that conditions there are different. In the brief hours before sunrise, the temperatures at the summit calderas drop low enough for water vapor in the air to settle out as tiny patches of frost. It is a thin layer, only about 1/100th of a millimeter thick. Across the wide summit calderas, that adds up to about 150,000 tons of water, moving back and forth between the air and the ground every single day during the cold season. A whole cycle of evaporation and freezing happening at the top of mountains, taller than anywhere on Earth, on a planet where almost no liquid water has flowed for billions of years. This is the kind of finding that quietly changes a planet. Mars had been thought of for a long time as a place where water cycles only at the poles. The discovery of frost on Olympus Mons means that, even now, there is moving water at the equator. A small amount, a whisper. But it is happening every Martian morning. The frost reaches your imagination because it is so familiar. A frosty window pane on a cold winter day on Earth looks almost the same as a frosty Martian rock in the morning. The patterns are the same. The crystals form in the same way, because the physics of water freezing out of an atmosphere is the same wherever there is an atmosphere thin enough to hold a little moisture. So there is a quiet image to hold here. Somewhere on Mars right now, in some shaded hollow, the temperature has just dipped below the right threshold. Water vapor in the thin air is settling onto a rock. A delicate layer of frost is forming. It is whitening, faintly, against the rust-coloured stone beneath it, and in a few hours, when the sun comes up and the air warms by a few degrees, the frost will lift back into the atmosphere, and the rock will be dry again. As if nothing had happened, as if the morning had been imagined. But it happens every Martian morning in different places, all over the planet. A small ritual of cold and warmth. A planet's way of saying good morning to itself. But not every Martian morning is so quiet. A few times in every Martian year, in the warm months when the southern hemisphere is closest to the sun, something else happens. The same wind that lifts those small whirls of dust at the canyon's edge starts lifting more of it. More dust, lifted more widely, in ways the planet rarely does at any other time. What begins as a regional dust storm in one part of Mars can, under the right conditions, spread. Not over hours, over weeks. The storm fans out across deserts, climbs out of basins, crosses ridges. The dust rises higher and higher into the atmosphere until it is no longer settling back down at night. It stays in the sky, and then, somehow, the storm crosses some threshold the planet has never quite explained to anyone, and it becomes global. Within a few weeks, the entire surface of Mars is wrapped in haze. From orbit, you can watch it happen. You can see the planet's familiar landmarks. The dark patches of basalt, the bright streaks across the plains, the great canyons and the volcanoes, slowly fading under a thickening orange shroud. One by one, the features go. The poles, Valles Marineris, Olympus Mons, all swallowed under the same orange shroud. After a few weeks, looking down from a spacecraft, you would see only an almost featureless butterscotch ball, with the faintest hints of structure where the highest mountains barely poke through. These are called global dust storms, and they happen on no other planet in the solar system. They are big enough to be one of the things you can identify Mars by from very far away. We have seen several of them up close. The first global storm we ever observed was in 1971, when Mariner 9 became the first spacecraft to orbit another planet. It arrived just as a global dust storm was starting. For weeks, Mariner 9 took pictures of essentially nothing. An orange disk, no detail. The scientists on Earth had to wait for the storm to clear before they could begin mapping the surface they had come to study. A more recent one, in 2018, was the storm that ended the Opportunity rover's mission. Opportunity had been working on Mars since January 2004. Nearly 15 years. It had long since outlasted its 90-day expected lifetime and had become, by then, one of the most beloved machines in the history of space exploration. When the 2018 storm began, the rover was on a routine task, and engineers told it to hibernate, to ride out the dust by going quiet. The plan was to wake it up when the sky cleared. The sky cleared months later. The rover never answered. Its solar panels, after so long, had simply not received enough sunlight during the storm to keep its electronics warm. Sometime during the storm, the cold had stopped it. NASA continued trying to contact it for months. In February of 2019, they announced the end of the mission. 14.5 years on Mars ended by a storm of dust. Standing inside one of these storms, on the surface of Mars, would be strange. The wind would not knock you over. We have already seen why. The thin air, even at 60 miles an hour, has very little force. But the dust would be everywhere. The sun, if you could see it at all, would be a small orange smear above. The shadows would soften and then vanish, because there would not be enough direct light to cast them. The whole world would dim into a flat, amber dusk that lasted for weeks. Then, slowly, the storm would clear. Dust would settle out of the sky, one tiny particle at a time. The sun would brighten. The shadows would return. The familiar butterscotch sky of an ordinary Martian day would reassert itself, and out across the plains, a thin new layer of fresh red dust would lie over everything that had been there before the storm came. Rocks, ridges, equipment, if any was left behind, all of it coated gently and uniformly by what the storm had been carrying. The storms are part of the long cycle of the planet. They redistribute dust across the surface. They wipe the slate. They erase tracks and bury footprints. And they expose, in their wake, surfaces that have not seen direct sunlight in a long time. A planet that storms once or twice in a year that lasts almost 2 of ours, and then, for the rest of that long year, quiet. When the dust does finally settle, the surface it lands on holds the memory of an older world. If you could lift the dust off Mars, scrape away the rust, and look at what is underneath, you would see something that does not match the cold, dry planet we know today. Riverbeds, lake floors, deltas, the wide fan-shaped structures that form where a river slows down as it spreads into still water. Dry channels carved into the rock by something that flowed. The evidence is unmistakable. Mars, billions of years ago, had liquid water on its surface. Not just a little. Whole rivers, whole lakes, possibly whole oceans. The clearest signs are in places like Jezero Crater, where the Perseverance rover landed in 2021. Jezero used to be a lake. You can see the delta clearly in orbital images, a great curving wedge of sediment laid down where a river once emptied its load into a body of standing water. The river is gone. The lake is gone, but the delta is still there, perfectly preserved in stone, billions of years after the water dried up. Across the planet, there are dry channel systems that look exactly like the dry river systems you find on Earth after a long drought. Wide, flat valleys with smaller tributaries feeding in. Meander loops where the water used to bend. Erosion patterns at the heads of canyons that look like waterfalls have collapsed inward, the way certain canyons on Earth grow as a stream cuts back into its own headwall. Some scientists believe that the northern hemisphere of Mars, which sits significantly lower than the southern, may once have held an ocean. The boundary between the high cratered south and the low, smooth north is one of the strangest features on the planet, and one's possibility is that this boundary marks an ancient shoreline. The smooth plains in the north would then be a former seabed. There are even features along the boundary that look, to some interpreters, like the worn coastlines of an ancient continent. We do not yet know if this is right. The signs are real. The interpretation is debated. But there is no question, from the rocks themselves, that water was a major force on Mars for a long time. When did this happen? Roughly 3 to 4 billion years ago. The wet period on Mars was during a stretch of time called the Noachian, named after a region on Mars that preserves rocks from that era. During the Noachian, the planet had a thicker atmosphere, warmer temperatures, and weather systems capable of producing rain and snow. There were storms. There were rivers running down into seas. There may even have been a planetary water cycle, the same kind we have on Earth, with evaporation and clouds and precipitation feeding the rivers. Then, slowly, that world ended. The atmosphere thinned. The temperature dropped. The water on the surface, deprived of the pressure and warmth that had kept it liquid, either evaporated into space or sank into the ground and froze. The rivers stopped running. The lakes dried up. The seas, if there were seas, retreated into permafrost beneath the lowlands of the north. The planet became what it is now, dry, cold, wrapped in its thin coat of dust. This did not happen overnight. It took hundreds of millions of years. Mars was very different at one point in its history. A Martian afternoon, 3.5 billion years ago, would have looked nothing like today. The sky might have been bluer. There would have been clouds. There might have been the sound of running water somewhere in the distance, the same sound any river anywhere makes. The riverbeds are still there. The deltas are still there. The lake beds, the shorelines, the meanders, all preserved in stone, all visible to spacecraft, all sitting under the rust, waiting for someone to look. Mars is a planet that has remembered everything. It has not forgotten its weather. It has not forgotten its water. It has carried on its surface the unhurried preservation of what it once was. And when humans first walk along the edge of an ancient Martian shoreline, kneeling to touch the sediments where a wave broke billions of years ago, they will be touching a record of a world that vanished almost completely and yet refused to be erased. There is still a question hanging over all of this, and it is the most important one. Why did Mars lose its water? Why did the rivers stop running and the atmosphere thin away? What turned a wet world into the cold, dry one we know today? The answer, as best anyone can reconstruct it, has to do with something we cannot see when we look at Mars. It has to do with a magnetic field that no longer exists. Earth has a magnetic field. You can feel it work, in a small way, every time you use a compass. The needle swings to point north because the planet itself, deep inside, is acting like a giant magnet. That magnet is generated by the slow churning of molten iron in Earth's outer core, about 3,000 kilometers below your feet. Electrically conductive metal, in motion, generates a field. The field reaches out far beyond the planet's surface, wrapping the Earth in invisible curving lines that arc from pole to pole. That field does something we almost never think about. It protects us. The sun is constantly throwing out a stream of charged particles, a fast-moving plasma called the solar wind. If those particles hit our atmosphere directly, they would, over billions of years, slowly knock the gas molecules in our upper atmosphere off into space. Earth would lose its air. The magnetic field deflects most of that solar wind away. It is a planetary shield. It is the reason we still have an atmosphere thick enough to hold liquid water on the surface. Mars used to have a magnetic field too. 4 billion years ago, Mars had a hot, molten iron core, much like Earth's. The same process that generates our magnetic field generated one around Mars. It was probably as strong as ours, or close to it. The early Martian atmosphere, the rivers, the lakes, all the warm, wet conditions of the Noachian period were protected by this Martian magnetic shield. Then, very slowly, the core cooled. Mars is a small planet, about half the diameter of Earth, less than 1/8 the mass. Small bodies cool faster than large ones because they have less internal heat relative to their surface area. The Martian core, deprived of the heat that kept it churning, lost its motion. Without motion, the dynamo stopped. Without the dynamo, the global magnetic field faded. By about 4 billion years ago, the protective shield was largely gone. And once it was gone, the solar wind began doing to Mars what it cannot do to us. It began to strip the atmosphere away into space. This was not a fast process. It was not catastrophic. It happened over hundreds of millions of years. The lighter gases went first, hydrogen and the lighter parts of water vapor. Then heavier gases followed. Without an atmosphere thick enough to hold pressure on the surface, the rivers could no longer flow. Water that had been liquid evaporated and got carried away with the air. Whatever was left, in the form of vapor or ice, sank into the ground and froze. The whole thing took the kind of time a planet's geology counts in, slow enough that there was no single moment of change. Just an unbroken, gentle bleeding of atmosphere into space, century after century. By the time anyone could have noticed, Mars was already mostly the planet we see today. The NASA's MAVEN spacecraft has measured what is left of this process. Even now, the solar wind is still chipping away at the thin remaining Martian atmosphere. Around 100 grams a second. Almost nothing on a planetary scale. But the process is real, and it has been going on for 4 billion years. There is a strange and beautiful detail in all of this. The dynamo is gone, but the rocks of Mars still remember it. Certain regions of the Martian crust, especially in the southern highlands, are still magnetic. The rocks that solidified when the field was still active preserved an imprint of the planet's old magnetism. The same way an old record preserves a sound that was sung long after the singer has gone. Spacecraft can detect these crustal magnetic stripes from orbit. They are the fossilized memory of a younger Mars, when the planet still had its shield, when the air was still thick, when the water still ran. So the story of Mars is in some sense the story of a smaller world that ran out of internal heat too soon, whose iron core, deep at the center, stopped its slow turning, whose magnetic field faded into silence, whose air, then water, then weather, followed quietly behind. A planet that lost what it could not keep, and became what it is now, red and cold and quiet, going around the sun in its long, slow orbit, still there tonight. There is one place on Mars where we are slowly reading that history, layer by layer, a specific crater, with a specific mountain inside it, where a small robot has been climbing patiently for more than a decade. The crater is called Gale, named after the Australian astronomer Walter Frederick Gale, who studied Mars in the late 19th century. Gale crater is about 154 kilometers across, formed by an impact billions of years ago, somewhere in the equatorial region of Mars. It is the kind of feature that looks unremarkable from orbit, a circle in the rock, a bowl. Nothing dramatic by Martian standards. What makes Gale crater extraordinary is what sits inside it. In the middle of the crater rises a mountain. Officially, it is called Olympus Mons. Informally and more commonly, it is called Mount Sharp, after the geologist Robert Sharp, who studied Martian terrain in the 20th century. Mount Sharp rises about 5.5 kilometers from the floor of the crater. It is taller than most mountains on Earth. From the rim of the crater, you cannot see the top of it. How a mountain ended up in the center of an impact crater is itself a story. Mount Sharp is not what was left when the crater formed. It is what was deposited inside the crater afterwards. Layer by layer, over hundreds of millions of years, sediment piled up on the crater floor. Some of it was carried in by water, back when water still flowed on Mars. Some of it settled out of the atmosphere as dust. Some of it formed in standing lakes that filled and dried, again and again. The mountain we see now is the result of all that material being deposited in horizontal sheets, then partially excavated by wind over the billions of years since. What this means is that Mount Sharp, like the layered cake of a polar cap, is a stacked record of Martian climate. The lowest layers, the ones at the foot of the mountain, were laid down during the wet Noachian period, when Gale crater held a real lake. Higher layers represent the slow transition to a drier world. The very top layers come from the cold, dry Mars we recognize today. A geologist climbing Mount Sharp from bottom to top would be moving forward through Martian time. Each step up the slope would be a step into a slightly drier, slightly colder epoch. This is exactly what the Curiosity rover has been doing. Curiosity landed in Gale crater on August 5, 2012, lowered to the surface by a sky crane in one of the most complex landings ever attempted. The site was chosen specifically because of Mount Sharp. The rover landed near its base and began rolling. Since then, it has spent more than a decade slowly climbing the lower slopes, drilling into different layers, analyzing what the rocks are made of, and sending the data back home. The findings have changed our understanding of Mars. Curiosity has confirmed that Gale crater once held a freshwater lake, with conditions that, by the standards of early Earth, would have been habitable. It has found clay minerals, the kind that only form in the presence of liquid water. It has identified organic carbon compounds in mudstones. It has measured the radiation environment on the Martian surface, the temperatures, the seasonal weather, the wind patterns. It has photographed sunrises and sunsets and dust devils crossing the landscape. Curiosity is nuclear-powered. It does not rely on solar panels, while other rovers have been silenced by dust storms or by failing batteries. Curiosity's has a small radioisotope generator inside it that produces electricity from the slow decay of plutonium. It will keep producing power for years to come. The rover, in some sense, has its own internal sun. Mount Sharp is still mostly above it. After more than a decade of climbing, Curiosity has reached only the lower kilometers of slope. The summit, 5.5 kilometers up, is still out of reach. It will probably remain so, but every meter Curiosity travels takes it through a slightly newer layer of Martian rock, a slightly more recent moment in the planet's slow drying out. And so, somewhere on Mars right now, on the gentle lower slopes of a mountain inside a crater, a small wheeled machine is rolling forward at less than walking pace, reading the stones, telling us, slowly and one layer at a time, the story of what happened here. Curiosity is not alone up there. There are other machines on Mars, doing their own quiet work, some still active, some long since silent. The fleet has grown slowly over decades. Each one arrived as a kind of letter, taking months to fly between the planets. Each one landed in a different region. Each one had its own mission and its own way of looking at the world it had been sent to. Perseverance is the newest of the major rovers. It landed on February 18th, 2021, in a crater called Jezero on the northwest edge of a large region of Martian highlands. Jezero is the crater we mentioned earlier, the one with the perfectly preserved river delta. Perseverance was sent there specifically because Jezero used to be a lake, and a lake fed by a river is one of the best places to look for chemical signs of ancient life. The rover is bigger than Curiosity, slightly heavier, and built for a different kind of work. It carries a drill that bores cylindrical cores into Martian rock. Each core, about the size of a piece of chalk, gets sealed inside a small titanium tube and stored. Over the course of its mission, Perseverance has been gathering dozens of these sample tubes, drilled from carefully chosen locations across Jezero. Some it carries is inside itself. Others it has dropped onto the surface in small caches, marked for future retrieval. The plan is to bring them home. A future mission currently being designed by NASA and the European Space Agency will travel to Mars, pick up some of these sealed tubes, and launch them back to Earth. If it works, it will be the first time anyone has ever returned material from the surface of another planet. Once the samples arrive, scientists with laboratory equipment far beyond anything a rover can carry will spend years studying them in detail. Perseverance carries something else worth mentioning. When it landed, it brought a small companion, a helicopter, the first aircraft ever flown on another planet. Its name was Ingenuity. It was tiny, about the size of a tissue box, mounted on 4 spindly legs, with 2 rotor blades stacked on top of each other. Total mass about 1.8 kilograms. It looked, frankly, like a toy, and the problem it was sent to solve was, by every measure, considered very hard. Flying on Mars is difficult because the atmosphere is so thin. There is barely any air for a rotor to push against. To generate enough lift to leave the ground, Ingenuity had to spin its blades at around 2,500 revolutions per minute. That is roughly 5 times faster than the rotor speed of a typical Earth helicopter. The first flight in April 2021 was a 39-second hover, only about 3 meters off the ground. It was the first time a powered, controlled flight had ever taken place on another world. Ingenuity was supposed to fly 5 times. It flew 72. For nearly 3 years, it kept going. It scouted ahead of Perseverance, photographing terrain. It flew higher and faster than its designers had expected possible. By the end, it had survived dust storms, frozen nights, mechanical wear, and a Martian winter that had not been part of the original mission plan. It became, in the quiet way that machines sometimes do, beloved by the people who worked with it. In January 2024, on its 72nd flight, Ingenuity damaged a rotor blade during landing. The damage was not catastrophic. The helicopter was still on the surface, still able to communicate. But without an intact rotor, it could not fly again. NASA officially retired Ingenuity later that month. The helicopter is still on Mars, sitting where it landed for the last time, photographed once by Perseverance from a distance, a small, silent companion to a much bigger rover, both of them resting in a crater that was once a lake. There are other machines too, orbiters circling the planet, taking pictures, mapping the surface, measuring the atmosphere. NASA's MAVEN, the Mars Reconnaissance Orbiter, the European Mars Express, and others. Some of them have been at Mars for nearly 2 decades. They watch the dust storms come and go. They map the polar caps. They send back the photographs that all of us, eventually, get to see. And down on the surface, the rovers go on rolling. Curiosity climbs its mountain. Perseverance drills its rocks. Ingenuity sits quietly in the dust. Together, they make Mars in a way it has never been before, almost a populated world. One of those rover cameras did something simple a few years ago that turned out to be quietly extraordinary. It pointed back at us. On the evening of January 31, 2014, Curiosity finished the day's drive and turned its camera, just before its instruments dimmed for the night, toward the western sky. The sun had set about an hour earlier. The Martian twilight was still soft and glowing, and there, low in the sky, was a small bright point. It was Earth. The image Curiosity sent home shows a pale blue star, with a fainter point of light next to it. The fainter point is the Moon. From the surface of Mars, our planet and its companion are not separable to the human eye. They appear as one bright object with a smaller companion, brighter than any other star in the Martian sky, sitting above the rocks of Gale Crater. Earth, seen from Mars, looks the way Venus looks from Earth. A vivid, steady glow, slightly tinted blue rather than white. It would not be hard to find. If you were standing on the rust-coloured ground, and you knew where to look, it would be the brightest, unmoving point in the morning sky just before sunrise, or in the evening sky just after sunset. The same place we look for Venus from our own porches. There is a long tradition of photographs like this. In 1990, the Voyager 1 spacecraft, on its way out of the solar system, was asked by Carl Sagan and others to turn its camera back toward the inner planets and take a parting picture. Voyager was 6 billion kilometers away when it took that image. Earth, in the resulting photograph, was less than a pixel wide, a tiny blue speck suspended in a thin band of scattered sunlight. Sagan wrote about that image afterwards. He called it the pale blue dot. He wrote about how every human who has ever lived, every war and every love story, and every empire took place on that small speck of light. He wrote about the importance of perspective, about how the universe does not see us as important, about the gentle invitation of distance to look at our world differently. The Mars photograph is a much closer cousin of the Voyager one. From Mars, Earth is not less than a pixel. It is a visible point. It is the size and brightness of an ordinary star. You can almost see the geometry of our planet, our atmosphere, our companionship with our own small moon. But it is still tiny, still distant, still a blue point of light in the sky of another world. There is something about that view that is hard to describe. The blue is the blue of oceans, of water that has not gone away the way it went away on Mars. The brightness is the brightness of an atmosphere thick enough to reflect sunlight strongly. The fact that you can see it at all from Mars is a reminder that we are not so far apart. A spacecraft can cross that gap in 6 to 9 months, a photon of light in a dozen minutes. If you were standing on Mars tonight, after sunset, in the long blue twilight, you could look up and find Earth without any equipment. Just step outside. Let your eyes adjust to the darker Martian sky, and there it would be, a bright, steady point of blue, the world you came from, the world where your friends and family are looking at the same sky from the other side, finding the same point of light, only this time it would be red. 2 planets, 2 points of light, looking at each other across the empty space between, each one tracing its own orbit around the same sun, each one from the other's surface, a single quiet star. We have always been able to see Mars from Earth. We are only now learning to see Earth from Mars, and the image, when you look at it long enough, has the same quality the Voyager image had, a kind of stillness, a kind of distance, a reminder that home from the outside is small. There is one question we keep coming back to. It is the question every photograph of Mars, every drilled core, every careful instrument is, in some sense, asking. The question is whether, on that distant, rust-coloured point of light, anything ever lived. The honest answer is that we do not yet know. What we do know is that the conditions for life were once present. We know that Mars had liquid water on its surface for hundreds of millions of years. We know that water was, in places, fresh and pH neutral, the kind that would have been drinkable. We know that the early Martian atmosphere had carbon dioxide, nitrogen, and at least trace amounts of the other ingredients you need to build organic chemistry. We also know that Mars had the time. Life on Earth seems to have started within a few 100 million years of the planet cooling enough to allow liquid water. Mars had its warm, wet period for at least as long. If life is something that emerges easily, given the right ingredients, it would have had a chance to emerge on Mars too, twice in the same solar system, independently. That is the conditional case. As for the evidence itself, the picture is partial and intriguing, rather than conclusive. Curiosity, during its years climbing Mount Sharp, has found organic molecules in Martian rocks. These are not life. They are the carbon-based building blocks from which life on Earth is made. Things like benzene rings, simple chains of carbon and hydrogen, and other molecules that biology uses, but that can also form by non-biological processes. Finding them does not prove anything happened. It does prove that the chemical ingredients were available. There is also methane. Methane is a gas that, on Earth, is mostly produced by living things. It is what cows breathe out. It is what swamps release. It is also produced by some geological processes, but much more rarely. On Mars, traces of methane have been measured in the atmosphere by Curiosity and by orbiters above the planet. The amounts are small. The amounts also seem to change with the seasons. Sometimes there is more methane, sometimes there is less. And methane in the Martian atmosphere should not last long. Sunlight should be breaking it down within a few centuries at most. So whatever is producing it now in some quantity, somewhere. Nobody knows what the source is. Living microbes deep in the Martian subsurface, surviving in pockets of water below the permafrost, are one possibility. Geological processes involving rock and water deep underground are another. Both are consistent with the data. Neither has been confirmed. The samples that Perseverance is collecting in Jezero crater are meant to address this question more carefully than anything before them. The sealed titanium tubes contain pieces of an ancient lake bed, drilled from rocks that formed in the kind of water that, on Earth, would have been teeming with microorganisms. If life ever existed on Mars, traces of it might be in those tubes. Chemical signatures, faint structures, isotope ratios that biology tends to leave behind. The kind of evidence that a rover, by itself, cannot easily detect. If those samples come back to Earth and are studied with all the laboratories we have, we may, within the next decade, have an answer to a question humans have been asking for thousands of years: whether life on Earth is the only kind in the solar system, or whether it once happened somewhere else too. Whether biology, given the right ingredients, just happens, or whether it is rare, or whether it is unique. Either answer would matter. If we find evidence of past Martian life, it would mean that life is something that arises easily when conditions allow. It would suggest that the universe is, in some real sense, full of biology. There would have to be other places. Many of them. If we find that there was never any life on Mars, that the chemistry stayed chemistry, and never made the small mysterious jump to becoming a living thing, that would matter too. It would mean that life is harder than we thought, that what happened on Earth was, on the cosmic scale, special, that we are alone in our solar system, and possibly in many others. Either way, the answer is sitting quietly in sealed tubes on the surface of Mars, waiting. So we come back to where we started. A window, a night sky, and a small red point of light. You found it once already on the first night of this story. Now you have spent some time with it. You have learned what those ancient watchers in Egypt and Babylon could not. You have learned that it is a world. You have learned its colours and its weather, and the sound its wind would make against your skin. You have learned its mountain, its canyon, its moons, its frost. You have learned what it once was, and what it became, and what we are still trying to find out about it. The same small fell embers is still up there tonight, but now, behind it, you can see what is actually there. A volcano 2.5 times the height of Mount Everest, with slopes so gentle you would never know you were climbing them. A canyon long enough to stretch across the United States, cracked open in an earlier age, when the planet's crust still moved. 2 small moons that look like asteroids, the inner one racing the wrong way across the Martian sky 3 times a day. polar caps that breathe carbon dioxide in and out of the atmosphere with each long season, a morning frost that forms in shaded hollows and burns away by mid-morning, dust storms that occasionally cover the whole planet in a soft amber dusk for weeks at a time. There are the dry riverbeds, still there, still preserving the lines of water that ran billions of years ago. There is the magnetic field that vanished, and the slow loss of atmosphere that followed. There is the rover slowly climbing Mount Sharp, layer by layer, reading the stones. There are the sample tubes of Jezero, sealed and waiting. There is a question we have not yet answered, and there is, every once in a while, an evening on Mars when a small rover camera turns its lens back toward Earth, and we see ourselves the way Mars sees us, a blue point of light in a Martian twilight sky. If you have made it this far, and if listening tonight has helped, please consider giving this video a like. It quietly helps more sleepy listeners find their way here. Subscribe. If you would like to come back for more nights like this one, when we will sit together and learn the unhurried patience of another corner of the universe. And if you have not yet told us in the comments where you are listening from, you still can. We like imagining the lights going off in different cities, in different time zones, all over our small blue planet, while we listen to a story about its quiet red neighbour. Mars is still up there. It is doing exactly what it has been doing for 4.5 billion years. Turning slowly once every 24 hours and 39 minutes, tracing its long eccentric orbit around the same sun we orbit, only a little farther out. Folding on to its rust and its thin air and its quiet, patient frost. Its mountain growing nothing taller, its canyon eroding nothing wider. The machines we have sent, some still rolling, others sitting silent where they last stopped. Tomorrow night, if the sky is clear where you are, you will be able to find it again. The same red point of light, the one the Babylonians named Nergal, and the Romans named Mars, and we have spent this last little while quietly visiting in our imagination. Until then, settle in. Let your shoulders fall. Let the room be quiet. Mars will keep doing what it does. The planets will keep turning. The light will keep arriving from across all that empty space, patiently, on its own schedule. Good night from here. Good night from there. Good night from a small red world 225 million kilometers away that has been waiting up all this time for someone to look.